Hello, this is Variational Inference, Part 3. I am Chieh from Northeastern University. So in today's video, now that we've gone through the basics, ideas that you need to understand, namely information theory, today we're going to mostly talk about why variational inference. Now, over here, we can see some graphical model, like right here. And I'm hoping that if you're doing variational inference, you already have a good idea of graphical models, at least the very basics of it. So if this is the graphical model, and here these arrows denote dependency. So if you want to find the joint PDF, so this is the joint PDF, like probability of x1, x2, x3, x5. It's just convenient to write 1 to 5, but they're the same thing. So if you want to find a joint PDF, like all you have to do is look at the graphical model in terms of its dependencies. So it will be probability of 5 given 3, see, 5 given 3, and then 4 given 2 and 3. So 4 given 2 and 3, right? And then 3 given 1, 3 given 1, and then 2 given 1, 2 given 1. And lastly, we just have 1 right here, probability 1, x1. So if we can somehow put a problem, a model with graphical model, it is quite easy to get a joint PDF. However, if we are looking for something different, something more like a continuous, a conditional distribution, instead of the joint PDF, we have probability 3 and 4 given 1 to 5. Now that is much more complicated because we have the joint, so that's known. We know this already, but then we got to do this integral, which I mean, depending on the function. If the function is easy, yeah, you can solve this integral, but very often you have a very complicated joint PDF. So solving this integral is sometimes not even possible. Like nobody knows how to do it. So how do you get a conditional distribution in those situations if you can't even solve for this? Well, wouldn't it be nice if we can just somehow get this like from the joint PDF and just completely go bypass solving the integral and just get this value, like the conditional? Is it possible? That's the question. Is it possible to go from joint to conditional without needing to solve this integral here? Well, yes, that's the answer. Yes, and that's the point of variational inference. Variational inference. That is the point. The point of variational inference is to bypass the need to solve this integral and just get the conditional directly from the joint PDF. Now, variational inference is not the only way to solve this problem. Like to solve like this problem I just explained to you, there are many other ways. Ways such as Metropolis Hastings. That's another way to solve the exact same problem. And the answer you get is exact. So you get a very good answer. It's a type of solution by sampling. So you like sample. And when you sample enough, it kind of gives you the answer. It is more accurate, but it takes quite a while to get the answer. And it's easy to understand. Now, compared to variational inference, it's not sampling, it's deterministic. So it's a good approximation, but it's less accurate, obviously, because it's an approximation. But again, I iterate, it's decent, and it takes less time to compute. It takes significantly less time, but it's rather hard to understand. So these are the pros and cons of different approaches. And another approach, which it's not that good, is a poor approximation. It's also deterministic. It's much less accurate. It's poor, approximation. But it's fast and it's very easy to understand. So these are the three approaches. I think there might be more, but these are the three main approaches, at least, that people sometimes use. But for today, our concentration is variational inference. So we're going to talk about variational inference. Remember from the last video, if we had given, right, if we had given this thing, green thing, which it's known, but right here, and this is the conditional. So we have the joint, we don't know the conditional. This is unknown. And we can't find this because the integral is very difficult to solve. So this is the problem. I know I've said this many times, but yeah, it's very often people don't really get the point of variational inference. They just jump in and try to understand the math. But well, in any case, since we don't know this, right? What we do is we use another function called Q of Z to approximate it. Now, remember, it was the same situation as last video. There's some conditional that we don't know, and we use Q of Z to approximate it. Now, when we're in a situation where we estimate a conditional with Q of Z, we can use the property of KL divergence, the relationship between KL divergence and law of P of X to help you. Now, remember, KL divergence measures the distance between two functions, two probability distribution. In this case, it's a measurement between the approximation here and what's being approximated. So the smaller the KL divergence, the smaller the error between the approximation and the destination. So, and from the last time, we know that this value is fixed because it was given. Remember, probability of Z given X. So X is given. So this value is fixed. But we can manipulate these two values by picking the right Q of Z. Now, remember, I showed you this table last time. These are fixed by manipulating the lower bound. This is the lower bound. Now, see how we're simultaneously reducing the KL divergence, right? So by increasing the lower bound, we're reducing the KL divergence. Okay, it's the same thing. Now, the KL divergence is here, and the lower bound is here. Oops, lower bound is here. Now, if we were trying to deal with the KL divergence, we have to deal with the conditional, which is, a pain, just a pain. But if we deal with the lower bound, we only need to deal with the joint PDF, right? So it's much easier to try to maximize the lower bound than to try to minimize the KL divergence. So we want KL divergence, this and this, to be as small as possible. This is the same as making the lower bound as large as possible. That's the point I just said. You want this as small as possible. This must be as large as possible. Therefore, to find the conditional, using variational inference, right? Variational inference finds Q of Z that maximizes the lower bound. That's the point. We are trying to find this. The goal of variational inference is to find these two, Q of Z, that maximizes this bound here. Okay? Well, this is actually still a very hard problem. Like, how do you go about finding this? I don't know. So in this video, I want to reiterate what we're trying to do in variational inference. Namely, we're trying to maximize this function here. Now, to do this, to maximize this function, we need to pick Q of Z. So I think I'm going to stop here. In the next video, we're finally going to jump into variational inference and see how we actually pick this Q of Z. Okay?